And the crazy part is, these systems are making literally billions of recommendations every single day. We're talking about LinkedIn suggesting you connect with your old roommate from freshman year, or Facebook surfacing that long-lost cousin you haven't seen since you were 5.
Billions. That's staggering. I mean, I get the idea of a social graph, but the sheer scale of processing that data must be insane. How do they even begin to manage something that massive?
Exactly. And it's not just about managing the data, it's about making relevant recommendations. Imagine if LinkedIn kept suggesting you connect with random people in completely unrelated fields. It'd be useless, right? That's why social graph machine learning is so critical. Without it, these platforms would just become noisy, unusable messes. Think about a world where Facebook's friend suggestions are totally irrelevant, or where LinkedIn can't help you find relevant connections for a new job. It would completely undermine their core value proposition.
Okay, so relevance is key, but what's the cost of getting it wrong? I mean, beyond just annoyance.
Think about user engagement and churn. If people aren't finding value in the platform because the recommendations are bad, they stop using it. That's lost revenue, lost ad impressions, and ultimately a failing business. Remember when Google Plus tried to compete with Facebook? One of the reasons it failed was because its social graph wasn't as robust or relevant. They couldn't surface meaningful connections, and people just didn't stick around.
Right, Google Plus, the social network that nobody asked for. So let's dive into the technical details. What are the core concepts we're talking about here?
First, let's talk about graph databases. Imagine your social network is a map. Each person is a city, a node, and each connection between people is a road, an edge. A graph database is specifically designed to store and query this kind of relationship-based data super efficiently. Instead of tables and rows, you've got nodes and edges.
Okay, that makes sense. So instead of running complex SQL queries across massive tables, you can directly traverse the graph to find connections. But how does that translate into actual recommendations? Let's say LinkedIn wants to suggest I connect with a specific person. How do they use the embeddings to make that decision?
That's where link prediction comes in. After generating the embeddings for all nodes, the system can predict the likelihood of a connection between any two nodes. You can calculate the distance between their embeddings in that high-dimensional space. The closer the embeddings, the higher the probability that those two people should connect. For example, if you and I have a lot of mutual connections, work in similar fields, and have interacted with the same content, our embeddings will be close, and LinkedIn might suggest we connect.
Ah, so it's a combination of graph structure, node embeddings, and then a prediction model on top. It sounds incredibly complex. What about scalability? How do they handle billions of users and connections?
Scalability is the biggest challenge, no question. One technique is graph partitioning, dividing the graph into smaller subgraphs that can be processed independently. Think of it like breaking a giant city into smaller neighborhoods. Another approach is using distributed graph processing frameworks like Apache Graph or GraphX. These frameworks allow you to run graph algorithms across a cluster of machines, massively increasing the processing power.
So they're essentially parallelizing the computation across hundreds or even thousands of servers. That makes sense. But what about real-time updates? Social networks are constantly changing as people add new connections, post updates, and join groups. How do they keep the graph and the embeddings up to date?
That's where incremental updates come in. They can't afford to recompute the entire graph every time someone makes a change. Instead, they use algorithms that can efficiently update the embeddings based on local changes in the graph. For example, if you connect with someone new, they only need to update the embeddings of you, your new connection, and your immediate neighbors.
Okay, so it's a combination of clever algorithms and distributed computing infrastructure. It's impressive how much thought goes into something that most people take for granted. But wait, doesn't the freshness of the data matter too? Wouldn't a week-old embedding be less accurate than a real-time one?
Absolutely. And here's where it gets interesting. There's a trade-off between accuracy and computational cost. Recomputing embeddings in real time for the entire graph is simply not feasible, so they have to strike a balance. They might update the embeddings more frequently for active users or for nodes that have undergone significant changes. They also use techniques like caching to serve pre-computed embeddings for frequently accessed nodes.
So it's a constant balancing act between accuracy, freshness, and computational cost. It sounds like a really hard optimization problem. Are there any ethical considerations that come into play? I mean, these algorithms are essentially influencing our social connections.
That's a crucial point. Bias in the data can lead to biased recommendations. For example, if the training data disproportionately represents certain demographics, the algorithm might be more likely to suggest connections within those groups, reinforcing existing inequalities. Think about Amazon's recruiting tool that was found to be biased against women. The same kind of bias can creep into social graph recommendations.
Right, so you need to be really careful about the data you're using to train these models. What are some practical takeaways for software engineers working on similar problems? What should they do differently after listening to this?
First, think graphs first. Don't try to shoehorn relationship-based data into relational databases if a graph database is a better fit. It's like trying to fit a square peg in a round hole. It might work, but it'll be messy and inefficient.
Makes sense. What's the second takeaway?
Second, embrace embeddings. Node embeddings are a powerful way to represent complex relationships in a way that machine learning algorithms can understand. Experiment with different embedding techniques and find the one that works best for your specific problem. It's like finding the right key for the lock. It can unlock a whole new world of possibilities.
And the third?
Third, monitor for bias. Regularly audit your data and your algorithms for bias. Be aware of the potential for unintended consequences and take steps to mitigate them. It's like checking your brakes before you drive. It can prevent a serious accident.
Great actionable advice. So to recap, we've talked about graph databases, node embeddings, link prediction, scalability challenges, and ethical considerations in the context of social graph machine learning. It's a complex field, but hopefully we've demystified it a bit.
Exactly. And remember, the social graph is more than just a network of connections. It's a reflection of our relationships, our interests, and ultimately who we are.
It's like a digital mirror reflecting our social selves.
And that's the power and the responsibility that comes with building these systems.